Hi children, so today let us see a very interesting topic, that is nuclear fission. Nuclear fission reaction. So usually nuclear reactions are those reactions when a nucleus of less stability will transform itself into a more stable configuration. Will transform itself through any kind of reaction to attain a more stable configuration. So first let us see nuclear fission. Nuclear fission is generally that category of nuclear reaction where a heavy nucleus which is unstable splits into two lighter nucleus. Okay, so usually the nuclear fission reactions are of very much importance or great importance in the field of research study in the case of nuclear reactors and all. So let us first see a detail how a nuclear reaction takes place in the case of a nuclear reactor. So usually in a nuclear reactor, the fuel used is uranium 232, sorry, 233, uranium 235, or it can be plutonium 239. So these are the three types of fuels which are used in a nuclear reactor. So first let us see what is the basic reaction, nuclear reaction inside a nuclear reactor. It is a chain reaction. A chain reaction is one in which one particular reaction, the product coming out of the first reaction will initiate further reactions and it will go on indefinitely. So this is known as a chain reaction. So in the case of a nuclear reactor or the nuclear reaction, in the case of a nuclear fission reaction, let us first take the case of uranium 235, which is undergoing fission when slow neutrons or thermal neutrons come and bombard these uranium 235. So when uranium 235 is bombarded with slow neutrons or thermal neutrons, it actually gets transformed or split into two lighter nuclei, the barium and krypton. You can see the mass number 141 and 92, and along with that it releases three other neutrons, fast moving neutrons, plus enormous amount of energy per fission reaction. So this is what happens in one particular fission reaction. When a neutron bombards uranium 235, it will split into barium and krypton, and three other neutrons are also released, plus an enormous amount of energy. Usually it can it we cannot say that for definitely that only barium and krypton will be released. There are other several other elements also into which it can the nucleus can split into. So the probable reaction is splitting into barium and krypton. Now, uranium 235 is an isotope of naturally occurring uranium. Naturally occurring uranium is 238. That is 1 kilogram of naturally occurring uranium is uranium 238 will have almost a 0.7 percentage of U235. But the fuel which has to be used in nuclear reactors and all, we have to increase the percentage of this uranium 235, because the disadvantage of using natural uranium is that uranium 235 can undergo fission reaction only with fast moving neutrons. So that is a less probable case. So but this uranium 235 will can have its nuclear fission reaction initiated even with slow moving neutrons. So that is the advantage of having uranium 235 as the fuel of a nuclear reactor. Now, what happens basically inside a nuclear reactor is a chain reaction, which is a controlled chain reaction. So as this chain reaction can happen indefinitely or continuously, you know that this will go on increasing exponentially. So a nuclear reactor basically works on the principle of controlled chain reaction. So what a chain reaction is shown here, that is when uranium 235 is bombarded with one neutron, it will be releasing barium and krypton along with the three neutrons, and these three neutrons has a probability of hitting another three uranium nuclei, and this will again initiate further reactions, and these neutrons will again bombard other uranium nuclei, and this will go on indefinitely. But what might happen here is some of the electrons may be lost or leaked out from the reactor core, and they will not initiate a further reaction. So out of three, you can consider almost two neutrons may engage in further nuclear reaction due to the loss of neutrons or the leakage of neutrons from the reactor core to the surroundings. So that can also happen. Now, an uncontrolled chain reaction is the basic principle behind an atomic bomb or an atom bomb, where this chain reaction goes on indefinitely and it will lead to an explosion. So when these chain reactions are contained in a very controlled manner, then we can use this nuclear energy which is being released. You can see plus Q, that means some amount of energy is being released per fission reaction. So we can use this particular energy into constructive purposes or for generating. It can be used as a source of energy. So nuclear reactors are a very good source of energy, where which gives out an enormous amount of energy which can be used for other several purposes. So let us see the basic schematic diagram, or how does a nuclear reactor work. So this is the basic reaction which is happening inside a nuclear reactor. We use uranium-235 mostly as the reactor fuel, and instead of uranium, naturally occurring uranium, which is U-238, which actually has, you are using uranium-238 but with more concentration of uranium-235. So first let us see the basic idea behind its working. The first one you see is the reactor core, that is where you insert the reactor or the fuel rods. Fuel rods are metallic rods which contain pellets of uranium-235. That is uranium-238 enriched with uranium-235. That is whose percentage has been increased from 0.7 to almost to 0.3 percentage, or up to 7 percentage of uranium-235 is you can call that uranium fuel as enriched uranium, where the percentage of U-235 is more. So this is the reactor core. Now this reactor core has fuel rods. These are the fuel rods which contain the uranium-235, and you can see control rods here. Control rods. The basic function of control rods is to control the chain reaction happening inside the core, because if you don't control the chain reaction, which can multiply in a very fast manner, it can lead to explosion. So how can you control the chain reaction? That is by absorbing some neutrons from time to time inside the core. That is, per reaction 3 neutrons are released. So when the number of neutrons produced in a particular reaction exceeds a certain limit to that of the neutrons which are produced in the previous generation or previous reaction, then it may lead to a very fast or a rapid increase in the chain reactions, and it can even lead to an explosion. So the control rods are inserted from time to time in order to absorb the neutrons, which are fast moving neutrons which are produced inside the reactor core, and usually the control rods are made of heavy water or graphite. And they are used to control the reaction. So when we talk about the controlling chain reaction, we have to know about a quantity or a parameter which is known as multiplication factor. Multiplication factor. Actually, two things happen here. So as I told you, some of the neutrons may leak out in a particular reaction, after a particular reaction, and also some of the many of the electrons are neutrons are produced in a particular reaction. So this ratio should be in a very healthy mode, otherwise it is going to lead to an explosion. So how can you define multiplication factor? It is a simple ratio. The multiplication factor is a simple ratio where which gives the rate of production of neutrons to the rate of loss of neutrons. Rate of production of neutrons to the rate of loss of neutrons. How neutrons are lost? Neutrons are leaked out. They are lost in that manner, leaked out or absorbed by the coolant, absorbed by the control rods and all. Rate of production is that per each reaction, neutrons are produced. Per reaction, 3 neutrons are produced. So this ratio should be within a limited value, or it should be close to unity. Okay, so when it is equal to unity, it is known as the critical factor, critical, the mass corresponding to the fuel is known as the critical mass, and it is that when K is equal to 1, it is the reaction is said to be it is considered as critical. That is, it is close to unity means that rate of production is equal to the rate of loss of neutrons. So in this case, this will go, I mean, this will sustain a reaction. This will make the reaction to go on a steady state. It will go, that is, power will be generated in a steady state when K equal to 1. What happens when K is greater than 1? K is greater than 1 is a very dangerous situation where the number of neutrons produced is more and more, and it will go on initiating further reactions, and it can lead to an explosion. So this is a supercritical state which can be dangerous. And K less than 1, when K becomes when it comes to less than 1 value, what happens is this reaction will go on, I mean, will reduce in its rate, will go on decreasing in its rate, and eventually it will die out. So it should not be below 1, too much below 1, or it should not be greater than 1. These two factors, actually this will make the reaction to die out with time. This will make the reaction to happen in a very fast mode or a rapid manner, and will lead to an explosion, and it is always kept almost equal to unity with the help of this control rods. And you can also see moderators in between. Moderators are, the function of a moderator is to slow down the fast moving neutrons, because after each reaction the neutrons produced are fast neutrons, and fast neutrons has less chance of initiating a reaction with uranium 235. It can of course initiate a reaction with uranium 238, but ours is an enriched fuel, enriched uranium, which means that we want the uranium 235 nuclei to get into the reaction by the slow neutrons. So how to slow down the neutrons? That is done by moderators. Usually heavy water, D2O, D2O or water is used as the moderator. Moderator, the function is to slow down the fast moving neutrons and make the probability of bombarding the uranium 235 with the slow neutrons. So this is the reactor core, and the whole core is shielded with the concrete walls, because the leakage, in order to protect the surroundings from the high energy, the gamma rays or the radiations, it is actually protected with a concrete wall. Then you can see a pump here. Then there is a coolant. Coolant usually is water, and this coolant, that is, the large amount of energy is released per fission reaction. Approximately one fission reaction will give rise to 200 million electron volt of energy per fission. So this is happening exponentially, so it has to release enormous amount of energy even with the very small quantity of uranium fuel. So what this energy is released in the form of kinetic energy of the fission fragments. That is, fission fragments are the barium and krypton and the neutron, and also it is released into the surroundings in the form of heat. So this heat can be used to heat up water and to produce steam, and there is a steam turbine which is connected to the electric generator, which can be used for constructive purposes. So we have the heat exchanger, where this heat, the function of the heat exchanger is to have the heat released from the nuclear reactor core and use it for producing steam. And steam is moves to the superheated steam goes into the steam turbine, which is used to run an electric generator. So cold water is pumped from time to time in order for this process to get sustained for a long time. So this is a nuclear schematic diagram of a nuclear reactor. There are several parts to parts which work effectively, and we have four nuclear reactors in India. One is in Tarapur Atomic Power Station in Maharashtra. Then in Rajasthan we have Rajasthan Atomic Power Station, and Narora Atomic Power Station in UP, and Kalpakam Atomic Power Station in Tamil Nadu. So atomic power stations are very useful in the sense that it has advantages, and also unless it is not maintained in a or managed in a proper way, it can lead to chaos or it can lead to an explosion. So and it has the advantage that it releases enormous amount of energy from a very small amount of the fuel used in it. And they also have additional purposes, that they are used in nuclear reactors produce radioactive isotopes, that is the byproducts of these reactions give rise to radioactive isotopes, which in turn are used in medical field and in treatment medical industry and also in agriculture. And they can also be used for the propulsion of ships, aircraft, submarines, etc. They are also used to produce neutrons of high energy, which in turn is used in the treatment of cancer, etc. So nuclear fission reaction is the basic reaction that is taking place inside a nuclear reactor, and it is taking place in a controlled manner. So it is known as a controlled chain reaction. So this is the basic reaction of uranium-235. And you also have to consider multiplication factor, which decides the fate of the nuclear reactor, whether the reactions will go on and on or in a steady manner, or it will lead to an explosion, or whether the reactions will die out.